Okay, after we discussed some fundamentals regarding DNSSEC, so what are the reasons for this and why you should think about to implement this for your own external DNS, let's now jump into the basics of DNSSEC itself. So what it actually contains, how it is structured, what it is actually doing. And we would like to start with a brief overview what DNSSEC actually is and what it's doing. It's an extension to the traditional DNS implementation that is more than 30 years old. And extension means that in an infrastructure where some parts of the DNS are signed and some parts aren't signed, DNS is still working exactly the same like it does in the last couple of decades. So even if the entire DNS infrastructure is signed, but your DNS system is not validating the signatures, this doesn't matter, you still get an answer. And also the other way around, if you are validating signatures and there is a zone that isn't signed yet, then your recursive server is still able to provide an answer. So this can coexist in parallel. It is using an asymmetric cryptography, which is quite common nowadays, and it's used for two main things. So there is authoritative DNS and there is recursive DNS, and the authoritative DNS is signed with DNSSEC, and the recursive DNS is validating these signatures. So these are the main two parts of DNSSEC. And this signing and the validation of the signatures is the best thing that you can use to validate or to ensure that an answer was provided by the system that is responsible for such an answer, and that the answer itself wasn't modified on its way to your recursive DNS server. So the signing itself is just half of the magic. The validation of the signed data is the second half of the magic. DNS is based on eDNS, which is an extension mechanism for DNS. And in particular, it's eDNS 0 that comes into play. But DNSSEC is not encrypting your DNS data. So the data itself is still clear text. So it's still not confidential. It's like a phone book, and I'm pretty sure you haven't ever seen a phone book that is locked. So this is what DNS was made for. And in addition to this, it is ensuring that your data is transmitted in a standard process and that it wasn't modified on its way, but the underlying DNS server itself is still as vulnerable as it was before. So DNS security or DNSSEC is just one part of DNS security. DNS security itself starts with securing the host and the operating system and the application itself, and this is a completely different story, and we are providing a dedicated course just for the basics of DNS security. So that means even if you have DNSSEC implemented, somebody can still break into your authoritative DNS server and change some records to some malicious domains or whatever. And the only difference is that in that moment, this wrong DNS data is signed on a signed or within a signed DNS zone. So just ensure that DNSSEC is just taking care of the transportation of your DNS and not of the DNS server or the operating system or the application itself. The signatures are using timestamps. So in some scenarios, NTP is still quite important for in DNS infrastructure. So for example, if you are using transaction signatures for zone transfers or for stuff like that, NTP has always been something that you have to keep in mind. And nowadays, I would say, because systems are always communicating with each other based on certificates and stuff like that, a proper NTP implementation is needed, and this is also the case for DNSSEC. And the validation means that these signatures are proven by the remaining hierarchy of the DNS architecture or DNS structure. This means with all these signatures that a typical DNS response is much larger than it was before. So we will definitely, or in most cases, reach the limit of 512 bytes. We will see more TCP than UDP in our future DNS infrastructures, and the fragmentation of IP packages can happen as well. The OARC is providing a test server that you can use to identify if your DNS infrastructure right now is able to handle packages of that size, so packages that are needed to support eDNS. So here we see a basic example. So I'm using the well-known tool DIG to run a query for a TXT record against this rs.dns-orac.net domain, and I receive an answer that my DNS server, or the DNS server that I was using in this example, supports the required size of a package to support eDNS. Here are just two other examples where the size limit is way too small. So the system that I used in that case was not able to provide enough package size for eDNS. And the example in listing number 3 gives the indication that the packet itself has been fragmented, and these fragments were filtered. So this environment is not supporting eDNS as well. And you should actually try to test this in your infrastructure just to ensure that your DNS systems are future-proof. As I already mentioned, there is a difference between a recursive and an authoritative DNS server. So the recursive DNS server is accepting DNS data from the public internet. So this the role of the system is to provide answers to remote information, to DNS data that does not belong to the environment where the recursive server belongs to, and an authoritative system is providing such data for the public internet. So the authoritative system is providing the data that the recursive system is expecting or even accepting. So if somebody wants to provide malicious data to your DNS infrastructure, such an intruder has to ensure that your recursive DNS server is accepting data that was misconfigured by an attacker, for example. An authoritative system, on the other hand, will never ever return a signed answer. So if you are familiar with the different flags that you can see in a DNS package, and when you are using DIG, for example, to troubleshoot DNS traffic, you are aware where these flags are displayed, and there is a dedicated flag for an authorized or for an authenticated data, and this is a flag that an authoritative system will never provide, because authenticated data means that somebody checked if the answer that was provided is the right one, and this is something that an authoritative system will never do. An authoritative system will always answer with the authoritative answer flag, and because of that it will never ever provide such a signed answer. Because we are using this asymmetric cryptography, the cryptography is based on public key mechanisms. So what DNSSEC is doing in this scenario, it verifies that whatever information an authoritative system provided wasn't modified on its path to the recursive system, and that it was the actual authoritative system that was providing this information on first hand. So we have some hashes stored in DNS, and these hashes are quite useful because every time when you change the text, just small portions of the text that is going to be hashed, the hash value itself is changing tremendously, and so you can easily identify just smaller changes to something like this. Because it's an asymmetric algorithm, we have different keys that we use for encryption and for decryption. So the key that is used for encryption is the one that you keep for yourself, and the key that is used for decryption is the one that is available on the public internet, which means in the public DNS. And when we sign the information in our DNS zones, we will keep these as digital signatures, and we will learn in the next couple of slides where they are stored and how this actually works. To support DNSSEC and the DNS infrastructure that is more than 30 years old, we had to add some additional record types. First of all, we need to clarify what a resource record set is, because the signing of DNS is not based on each and every single resource record. We do this for entire resource record sets, and the resource record set means it's the same label with the same type but different data. On the right hand side in listing number 4 we can see this www entry of example.com. So the label is the same, it's www, the type is the same, it's an A record, but the data is different. So this is an resource record set. And actually on top of this line number 2 to line number 5, this is so-called, or these are so-called same as zone records. So instead of the white space, we could type in example.com 4 times. So even this would be an entire resource record set. And with the same label, that means that everything that is on the left-hand side of the record type it has exactly the same name. And it's not totally clear, but the TTLs of the resource records have to be the same as well to be a resource record set. But this is something that is not strictly followed as far as I have seen it in some implementations. So even if there are different TTLs specified for the same label with same type but different data, even with different TTLs in some scenarios, it's the same. It's also interpreted as a resource record set. And even if there is just one single resource record, if there's just one single label, even that label or this single resource record is an resource record set. So it's not the case that we can only sign resource record sets if they have multiple RData fields, even if there's just one single label, one specific type, and one specific data field, even that's a resource record. There are different keys used to implement DNSSEC. There is a so-called zone signing key, which is used to sign the authoritative data within a zone. And then there is a key signing key, which is used to sign the public portion of the zone signing key, which is stored in a dedicated resource record. It's even possible to combine this in one single key, in a combined signing key. So that means this is a key that is used as a zone signing key and it is used as a key signing key. There are a couple of pros and cons for CSK. I won't deep dive into this at the moment, and I will follow with the principle of a zone signing key and a key signing key, because this is something that you will run into more often compared to a CSK. To store the public portion of the key signing key and the zone signing key, a specific DNS record was implemented, and that's the DSKEY record. And this type of record is used for both, so for the zone signing key, for the key signing key, and yes, also for the combined version of it. The only difference with the zone signing key and the key signing key is the 15th bit of the flags that are specified in the RData field of the DNSKEY, and this is the secure entry point bit. So it's just a specific bit that is switched to 1 if it is a key signing key, or it's kept to 0 if it is a zone signing key. So this specific flag with a value of 256 means we are looking at a zone signing key. If it is 257, that means we look at a key signing key, and this is the one that you should find represented in the parent zone as well, but we will discuss the relationship with the parent zone a little bit later. If we take a look at listing number 5, we can see that our DNS zone example.com has a couple of keys, or DNS key records. There is one in line number 3. It's the zone signing key that is used in this specific DNS zone, and then there are 2 key signing keys, line number 6 and line number 9. So these are 2 different ones with 2 different IDs, and this is quite common to keep more than one key signing key for redundancy reasons. To store the digital signatures for resource records, we created the RRSIG record, so the resource record signature, so a dedicated record type that is used to store signatures. And in listing number 6, we can see the resource record set of www.example.com. So here's just an example that this is a resource record set that contains only one single record, so there are no additional data fields, and the signature of this is displayed in line number 5 and below. So it has exactly the same name like the resource record that it is signing. It contains a couple of values right after the record type. So record type RRSIG, and then we have what type of records are covered by this resource record signature. So in that case, it's the A record. If we have multiple records like A record, quad A record, MX record, NS record, then we will see what kind of records this signature is used for. Then we have the algorithm, we have some labels, we have the original TTL that was assigned to the A record before, and then we have a couple of values when this signature starts to be used and what is the end of this signature. So that's actually the time frame when this signature is used. And then we have a couple of other values that we don't have to deep dive in right now. So just to give you an idea how such a digital signature for a resource record set could look like. To create a trusted hierarchy in the DNS infrastructure, which is called the chain of trust, we need a relationship between the different DNS zones. So from the root to the TLDs, from the TLDs to the second level, and so forth. To create something like this, a dedicated record was invented, and this is the delegation signer, the DS record. So this is stored in the parent zone, and this contains a hash value of the public portion of the key signing key. So the key signing key is the one that we used to sign our zone signing key, and a hash value of this one is stored in the parent zone. So if we see a DNS zone that is signed, if we take a look at the key signing key within that DNS zone, we can take a closer look at the parent of this zone if the delegation signer in that zone matches the key signing key that we saw in the child zone. A huge problem here is that this delegation signer has to be installed in the parent zone in some way. So it's very critical that you use a secure transfer mechanism to bring such a delegation signer to your parent zone. So sometimes you can do this over an encrypted portal. I have even heard about people that are using a USB stick and they drive to their parent zone's organization to actually give this to somebody in person. So it really depends how your parent zone, or what your parent zone is, who is responsible for this parent zone, and if they have implemented something that can be used to transfer the delegation signer in a secure way. At the bottom, we can see the delegation signer. So this is the part of the key signing key that needs to be stored in the parent zone. And here we see what is the actual owner. So in that case, it's the second level domain. And then we have a key tag, which identifies the key itself, the algorithm, and some additional values that are useful as well. But we don't have to deep dive into this right now. We just want to ensure that you understood that the delegation signer is the fundamental part that is used to create this so-called chain of trust. It's quite easy to provide an answer in DNS for something that exists. And in standard DNS infrastructures, it's also easy to provide an answer that something doesn't exist. But if we start to sign our DNS zone, we have to ensure that even such a negative answer is signed as well. And there are two possibilities to do this. There is NSEC and there is NSEC 3. NSEC means that you are sorting all your entire DNS zone, and for every single DNS record you create an NSEC record, which means what is the next record that comes right after this. So if you have DNS records A, B, C, and E, the NSEC record for C would be E, because D doesn't exist. And because that's the easiest way to create and proof of non-existence in DNSSEC, you can actually use this approach for something that is called zone working. So you start with A, and then you go with A, then with AB, and then you go with AC, AD, and so on. So you are just using all possible values to identify what kind of DNS record actually exists. And this is quite easy for NSEC. But in addition to this, this is also possible for NSEC 3. NSEC 3, instead of pointing a record to the next entry in the DNS zone, it is using hashes. So instead of providing the answer what the next record in the DNS zone would be, it just provides you a hash value that you can't really use for something, but you can use the answer for a non-existence of a query or of a record that one of your systems queried. At a footnote of this slide, you can see that somebody actually implemented an NSEC 3 worker. So the same that we did with the zone walking in NSEC is also possible with NSEC 3. It's just a little bit more complicated and it needs a little bit more horsepower. Something that you have to keep in mind is that we are talking about public DNS. And DNS is the phone book of the internet. And sure, we can hide things in our DNS zone with NSEC 3, but it's public DNS anyway. And with this NSEC 3 walker, it's even possible to walk through an entire DNS zone, even if it is NSEC 3 signed. So it's very, very resource hungry. So the signing process needs more resources. Transfer of the data needs more resources. The calculation of the NX domain responses takes more resources. So it means more CPU and memory are involved on your authoritative systems and on the recursive systems. And the question is if this is really worth it, or if we just keep it simple with NSEC, even if somebody would be able to walk our entire zone, but it's public anyway, so it just takes time to get the answers anyway. As I mentioned earlier, a major problem is to inform the parent of your DNS zone about the delegation signer. And we will talk about key rollovers in one of the later modules. But as we just saw, the two different types of keys, the zone signing key and the key signing key, technically they could stay forever. So you can just sign your zone and then you can keep these signatures forever. But it could be that you are using an algorithm that is maybe no longer supported in 10 years from now, or maybe the algorithm that you used is something that is easy to break meanwhile, because when you implemented it, it was quite secure, but 2-3 years later, somebody was able to break this kind of algorithm. So from time to time, you have to update your keys, your zone signing keys and your key signing keys. The zone signing key is quite simple. We will talk about this a little bit later, but the key signing key always involves that you inform your parent about the new delegation signer. And there is no standard process for this. So if you have a bunch of DNS zones, if you have yourcompany.de, yourcompany.com, yourcompany.net, yourcompany.org, yada yada yada, that means the TLDs are managed by different organizations, and each organization has a different way to handle delegation signers. And the CDS or CDS key record tries to fix that. It's a dedicated record that you can store in the DNS zone, in the child zone, that gives an indication to the parent that there are new keys available, and the content of such a CDS record is the actual DS record. So within assigned DNS zone, you will find the delegation signer and the CDS, which can be loaded by the parent zone to automate the process of updating the delegation signer. And as you can see in listing number 9, we have our key signing key. So we can identify this by the record type DSKEY and the flag value of 257. And in addition to this, there is a CDNS key, which is exactly the same, but the parent zone of this, which is .com, can use this key to, or can monitor for such keys to identify if new delegation signers are available. And if we take a look at line number 7, there is the actual delegation signer within the child zone. And in addition to this, there is a CDS key, which is exactly the same. So these are the two things that are the indication for the parent to update the delegation signers periodically. So now we understood what DNSSEC is actually doing, what types of DNS records are involved in this, and what types of records we use to create the so-called chain of trust. And the trust model itself is the next topic in our slide deck. So the chain of trust is related to the DNS hierarchy. At the beginning of this course, in the section of the DNS fundamentals, we had a quick look into the DNS hierarchy, which starts in the root, and then there come the TLDs, the second level domains, and so on. And the signatures that are stored in the RRSIG records are used to sign each and every single resource record set, and this is done with the zone signing key. The zone signing key itself is a DNS key record, so it is a DNS record, and this DNS record is signed by the key signing key. The public portion of the key signing key is transferred into a hash value, and this hash value is our delegation signer, which is stored in a DS record in the parent zone. And in the parent zone, the DS record is signed with the zone signing key of the parent, and this, on the other hand, is signed with the key signing key of the parent zone. And if we just take a look at the diagram on the right hand side, at the bottom we can see the different types of resource record sets that are signed with the zone signing key. And then we can see that the key signing key is used to sign the zone signing key itself, so the DS record of the zone signing key. Then we create a hash of the public portion of the key signing key, and this hash is transferred in a secure manner to the DNS of the TLD, which is in that case a .com. And this delegation signer is signed with the zone signing key of the TLD DNS zone, which again is a DNS key record, which is then signed with the key signing key, and this again on the next level, so the parent of this one would be the root DNS. They follow the exact same principle, and this is how we can create a chain between each and every single zone and subzone and subzone of the subzone, because we are always following the same principle that we are signing records, we are assigning the key that was used to sign the records, we create a hash of that key, and we transfer this to the parent so that this kind of a chain can be established. Now let's try to create such a ping pong of the DNS resolution in a nutshell. So on the left hand side we can see a validating resolver, and on the right hand side we can see the authoritative DNS server of example.com. So we just query for an A record, and in that case we query for example.com. And the authoritative system provides the answer, which is an A record or maybe a quad A record, plus the signatures, so the RRSIG of that record. Because it was a signed answer, the validating resolver has to validate the signatures. So it asks the authoritative system for the public key of example.com. The authoritative server is providing an answer for the public keys that were used to sign the example.com, which means this is the public portion of our zone signing key plus the signature of this DNS key resource record. In the next step, the system, so the validating resolver, is asking for the public portion of the keys that were used to sign the entire DNS zone, and the authoritative server is providing the answer what record was used to sign the zone itself. So in that case, the validating resolver has to validate if the key that was used to sign the entire zone, which actually means the key signing key in that case, by asking the parent zone for the public portion of the key signing key. And the answer would be the key for the specific DNS zone. And because the DNS zone itself needs to be signed as well, our validating DNS resolver is asking what keys were used to sign the TLDs, and the authoritative system is providing the answer what keys were used to sign the entire DNS zone itself. So in that case, again, it's a key signing key. And in the last step, because we have to follow the entire chain, the validating resolver tries to find out what were the public keys that were used to sign .com. So it's again checking with the root DNS server the delegation signer to be able to validate that the keys that were used to sign the zone and the keys that signed these keys are matching the delegation signer in the parent zone. So it's exactly the same process that was used between the zone example.com and .com. Now we see exactly the same one between .com and the root DNS. And at the end, the root DNS provides the answer, and in most cases, the DNS implementations are shipped with the public portion of the keys of the root servers, so the system will be able to validate these answers as well. And this is the entire process that the validating recursive server has to do every single time when it has to follow the chain of trust. The important thing to understand is that all these records and all these signatures are DNS records, so they have a TTL. So the validating recursive DNS server has not to follow the entire chain for all the time for every single query. So it will use the information in its cache, information that has been validated earlier, and because on the TTL it can assume that this information is still valid, so it's not going up the tree to the root for every single query, so just for the ones that it has to do.